For this lesson, you'll need your pencil, pen, or highlighter, your calculator multiplication table worksheet. We're going to do our 9.1a notes worksheet, and you may want to be writing additional information on a piece of paper. As we start working with our Intro to Trigonometry unit, we're going to review our concepts of working with radicals, whether we are simplifying, adding, subtracting, multiplying, and dividing. The best way to do this, think about our perfect square values. Perfect squares, they're an integer that's the square of that integer. So it's a product of some integer within itself. So on your multiplication table, we've highlighted your perfect square factors from our integers 1 through 25. It would make things a lot easier on you if you memorize the first 15 perfect squares. So we're talking about 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and 225. If you can remember these perfect squares, that will help in your simplification process. So what we're going to do is we're going to take a look at our warm-up here for 9.1a. Please pause the tape and try answering those 9 questions. For our question 1 through 6, it's asking us to write each number as the product of 2 whole number factors where one of the factors is a perfect square. So we want to think of the largest perfect square factors for each of those. So 12 would come from 4 times 3, with 4 being the perfect square factor. 27 would come from 9 times 3, with 9 being the perfect square factor. 50 comes from 25 times 2, where 25 is our perfect square factor. 48 comes from 16 times 3, where 16 is our perfect square factor. 72 comes from 36 times 2, where 36 is our perfect square factor. And 54 would come from 9 times 6, where 9 is our perfect square factor. For number 7, they're telling us if the square root of 7 squared is equivalent to the square root of 7 times the square root of 7, which is equal to 7, then what would the quantity 3 square roots of 7 squared be equal to? Well, anytime something is being squared, we have to remember that it's something times itself. So I'm going to write them so we have that each listed there. So as I'm looking at what's being multiplied together, I see that I've got 2 3's being multiplied together and 2 square roots of 7. So I'm going to rearrange those values so I have the 3's written next to each other and the square roots written next to each other. I know 3 times 3 is equivalent to 9. And based on my givens, I know the square root of 7 times the square root of 7 is equal to 7. So I can rewrite that as 9 times 7. Well, I can simplify that even further by saying 9 times 7 is 63. For number 8, what's the geometric mean between 8 and 12? This is pulling back on your geometry recollections here. When we talk about geometric means, we use these with our similar triangles, with our means extremes theorems. And so a quick reminder here, it's a proportional value where we say the product of the means is equivalent to the product of the extremes. If they're asking for the means, that means 8 and 12 must be the extremes, so we'll substitute those values in. And then follow our cross products operations here. So we're going to take our mean times mean, which would be mean squared, and 8 times 12, which would be 96. Well, we're asked to find the geometric mean. Well, if I have the mean squared, to undo that, I would have to take the square root of each side. Whenever we square root something that's being squared, that turns into the absolute value. And so the absolute value of our mean is going to be equivalent to the square root of 96. We have to remember that the absolute value measures the distance from 0, and we can move 2 ways on that number line. We can move to the left and to the right. When we go to the left of 0, we're working with negative values. When we're working to the right of 0, we're working with positive values. So I'm going to show each of those, going to the left and going to the right. And now we just have to undo each of these to solve for the mean. So for here on the left, I can divide both sides by -1, and so my mean will equal the square root, will equal negative square root of 96. And this one here on the right, we just need to divide by 1, so we have the mean equaling the square root of 96. For number 9, what is the square root of 7 divided by the square root of 7? Well, we recall from previous knowledge that anytime we have something divided by itself, the answer will always be 1. We're going to use those concepts reviewed in our warm-up to do some simplification of radicals and then work with the operations of them. So if we look at these first 4 problems here, we want to simplify these radicals. So we want to remember that they are coming from a product. So we're going to take the value and separate it from the product of 2 factors. And we would like one of those factors being a perfect square factor. So when we're working with the square root of 84, we have to think about what perfect square factor would work with 84. Well, we could divide by 4, which would leave us with 21. So if I write it as the square root of 4 times the square root of 21, I can simplify the square root of 4 into 2. And the square root of 21 does not have any perfect square factors. So my simplified answer would be 2 times the square root of 21. For our next problem, we have the square root of 63. So we have to ask ourselves, what perfect square value can we use with the square root of 63? Well, that would be 9. And we know 9 times 7 is 63. So we're working with the square root of 9 times the square root of 7. We know the value of the square root of 9 is equal to 3. So our simplified radical ends up being 3 square roots of 7. We're going to have you pause this video and try your numbers 3 and 4. For number 3, we want to simplify the square root of 24. We know 4 is a perfect square factor, and 4 times 6 is 24. We can simplify our square root of 4 to 2, so our answer would be 2 square roots of 6. For number 4, we're working with the square root of 72. We know our largest perfect square factor for 72 would be 36, and we can simplify the square root of 36 to 6. And we have our square root of 2. So our final answer would be 6 square roots of 2. Now that we know how to simplify our radicals, we're going to start working with their operations. We're going to see how we can add and subtract simplified radicals. So as we look at number 1, we're going to add the square root of 2 to square root of 2. We want to think of this as a simpler example. You've done this before in algebra and pre-algebra. Think of it as a plus a. We know a plus a would be equivalent to 2a. So using that same concept here, the square root of 2 plus the square root of 2, I have 2 of them. So I would have 2 square roots of 2. Please pause the video and try the next series of problems. For number 2, we've got square root of 2 plus square root of 2 plus square root of 3. If we want to relate it to a simpler problem, I can think of a plus b. I have 2 a's and a b, so that would simplify to 2a plus b. Well, here, my like terms would be the square roots of 2. I have 2 of them and only 1 square root of 3. So my simplified answer should be 2 square roots of 2 plus the square root of 3. For number 3, we have the square root of 2 plus the square root of 3 plus the square root of 3. Again, I can think it as a simplified problem where I would have a plus b plus b. These would be my like terms, so I would have a plus 2b. Here, these would be my like terms, the square roots of 3. So I would have the square root of 2 plus 2 square roots of 3. For number 4, we have 2 square roots of 3 plus 3 square roots of 3 plus 5 square roots of 2. I see that I have like terms with these square roots of 3. If I have 2 here and 3 here, I would have 5 total. So I've got 5 square roots of 3 plus 5 square roots of 2. These are not like terms, so I have fully simplified my expression. For number 5, we have 4 square roots of 2 plus 3 square roots of 3 minus 2 square roots of 2 plus 4 square roots of 3. By looking at this problem, I see that I have two sets of like terms, square roots of 2 and square roots of 3. So if I reorganize them by like terms, I can start simplifying my problem. So if I've got 4 square roots of 2 minus 2 square roots of 2, that would leave me with 2 square roots of 2. 3 square roots of 3 plus 4 square roots of 3 would leave me with 7 square roots of 3. For number 6, I have 4 square roots of 2 minus 3 square roots of 2. These are both square roots of 2, so they're like terms. 4 minus 3 would be 1, so I've got 1 square root of 2. For number 7, I have 4 square roots of 2 minus the square root of 2. Again, these are like terms. So if I have 4 here and I subtract 1, I would end up with 3 square roots of 2. We know how to simplify our radicals. We know how to add and subtract our radicals. We're going to take a look at how we can multiply and divide our radicals. And each time we want to try to relate it to a simpler problem, something that we've done before, and draw upon that experience. So let's take a look at the first one together here. For number 1, we want to take the square root of 2 times the square root of 3. We've used this before with our simplification. We had a value that we wanted to break into the product of two factors. Well, we have the factors. Let's see if we can put it back to the value. So if I have the square root of 2 times the square root of 3, I could write those both underneath one radical and then find their product. 2 times 3 is 6. So I have the square root of 6. When we're at this point here, we always want to think about, can we simplify the radical? Does 6 have any perfect square factors? In this case, 6 does not have any perfect square factors, so our simplified answer would be the square root of 6. Please pause the video and try the next set of questions. We have 3 square roots of 2 times 4 square roots of 6 times the square root of 3. We can see that we have values underneath our radicals and outside of our radicals. So just like we did before, we want to rearrange what's on the outside and what's on the inside to multiply them together. Three times 4, we know that value to be 12. Now we can multiply what's underneath the radicals together and see what that will simplify to. 2 times 6 is 12. 12 times 3 is 36. So we're working with 12 times the square root of 36. Again, at this point, you always want to ask yourself, can I simplify the square root of 36? Does it have any perfect square factors? In this case, 36 is a perfect square factor, so we know the value of the square root of 36 is 6. So I'm left with 12 times 6. And we know 12 times 6 has a value of 72. Number 3, we have the square root of 2 times the square root of 3 times the square root of 3. Since each of those is underneath a radical, we can write them as 1 and find their product. 2 times 3 is 6. 6 times 3 is 18. So we're working with the square root of 18. Again, at this point, you want to ask yourself, do you have any perfect square factors? In this case, we know 9 is a perfect square factor of 18, and so we're working with the square root of 9 times the square root of 2. We know the square root of 9 has a value of 3, and we will keep our square root of 2, so our simplified answer would be 3 square roots of 2. For number 4, we have the square root of 10 divided by the square root of 5. We're working with division here, which is just the inverse operation of multiplication. So just like we did before, we could write these underneath 2 individual radicals, but we also can write them underneath 1. So we could turn this into the square root of 10/5. And so we want to try to simplify this. 10 divided by 5 we know is 2. And so we're left with the square root of 2. For number 5, we've got 4 square roots of 2 divided by 2. Again, we can see that we have values on the outside of our square root, so they can interact with each other. So we know 4 divided by 2 is 2. And we still have our square root of 2, so our simplified answer would be 2 square roots of 2. For number 6, we have 4 square roots of 6 divided by 2 square roots of 3. We have values on the outside of our square root. We have values underneath our square root. And so we know that the outsides will interact with each other and the insides will interact with each other. We know that 4 divided by 2 is 2. And then we have the square root of 6 divided by the square root of 3. And we could, of course, rewrite that as 1 square root. 6/3 we know is a value of 2. So we have 2 square roots of 2 as our simplified answer. For number 7, we have the square root of 5 divided by 2. We could rewrite the division problem as a fraction and see if we can simplify it any further. The square root of 5 is underneath our radical. The 2 is not. They cannot interact with each other, so this would be our simplified answer, the square root of 5 divided by 2. For number 8, we have the square root of 3 divided by 5 times the square root of 5 divided by 5. We're multiplying two fractions together, and so we have to remember when we multiply fractions together, we multiply across. Numerator times numerator, denominator times denominator. So again, we've rewritten it to show that we're multiplying across. We have both of these values underneath the square root so they can interact with each other. So we have the square root of 3 times the square root of 5, which is the square root of 15. The square root of 5 times the square root of 5 is equal to the square root of 25. At this point, you always want to ask yourself, can you simplify your radicals? The square root of 15 does not have any perfect square factors. The square root of 25, we know 25 is a perfect square factor. So this has a value of 5. So our simplified answer would be the square root of 15 divided by 5. This process of what we've just done here is called rationalizing the denominator. Whenever we take a value, such as the square root of 3 divided by the square root of 5, and we multiply it by a value of 1. The square root of 5 over the square root of 5 has a value of 1. We are trying to rewrite our fraction so it no longer has a square root in the denominator. This value of 1 is not going to change the value of this fraction. It's just going to help us put it in a format that we can understand more clearly. We have a concept of what 5 is. Working with the square root of 5, unless you have a calculator, would prove to be difficult. So we're just rewriting the fraction in a format that we can understand a little bit better. Our radical work in trigonometry is very prevalent. And we've also seen working with radicals when we worked with our quadratic equations. So we're going to do a quick review on how we can solve our quadratic equations by factoring. I'm going to show you a fail-proof way on how you can factor every type of quadratic equation. You may have your own personal favorite method to use, and by all means, you are more than welcome to use that. Here I'm just trying to provide you with one way that you could use to solve for every type of quadratic equation. So let's do one together. For number 1, we have x squared plus 4x equals 5. When working with quadratic equations, when we want to solve by factoring, we always want to make sure that the equation is equal to 0. So we want to put it into standard form. In order to do that, we would have to move the 5 to the other side of the equal sign, and we would have to subtract it. So now we're working with our equation, x squared plus 4x minus 5 equals 0. The next step we want to do is look at the coefficient of our first term and our value of our constant. We're going to multiply those values together. So here my coefficient is 1. My constant is negative 5. 1 times negative 5 is negative 5. So I want to think of ways of what numbers could I multiply together to get negative 5, but will give me a sum of 4. Well, I know I can multiply 1 and 5 to get 5. And if I want to add them together to get a sum of 4, my 1 would have to be negative. So negative 1 times 5 will give me negative 5. Negative 1 plus 5 will give me 4. So I found two values that will help give us back this quadratic equation. What I'm going to do is rewrite the quadratic equation from 3 terms into 4 terms using these sum and product factors that we have here. So I keep my first term x squared. I keep my constant term as negative 5. And I want to group my two values so that they have something in common with each of those coefficients that we're working with. So I'm going to put my negative 1x here and my 5x here. So now I have 4 terms to my equation, which will still give me the value I started with, x squared plus 4x minus 5 equals 0. We're going to do a process here, factor by grouping. So I'm going to divide the equation to 2 parts. And I have now 2 halves. I'm going to take a look at each half and ask myself, what's the most I can divide out from each part? If I have x squared and negative x, I know I can divide out an x from both terms. If I'm working with 5x minus 5, I know I can divide out a 5 from both terms. So by dividing out those common factors, I have x times x minus 1 plus 5 times x minus 1. As I'm looking at this step in my process, I notice that x minus 1 is being multiplied by both x and 5. So I have a common factor to each part of my equation. So I'm going to factor out the x minus 1 and see what I'm left with. I'm left with x and 5. So now these are my two factors for my quadratic equation. X minus 1 times x plus 5 will equal 0. Now, this is being held together by multiplication. Whenever you multiply two values together and you end up with 0, one or both of those values will have to be equal to 0. So we take each factor and set it equal to 0. Once each factor is set equal to 0, we solve like we normally do. So if we have x minus 1 equals 0, in order to get x by itself, we would add 1. And so we have x equals 1. Here we have x plus 5 equals 0. To get x by itself, we would subtract 5. So we have x equals negative 5. At this point, let's have you pause the video and try the next series of factoring problems. For number 2, we have 2x squared minus x minus 1 equals 0. Our quadratic equation is set equal to 0, so now we can start working on factoring. We're going to take our leading coefficient of our first term, which is 2, and multiply it by our constant, which is -1. So 2 times -1 would be -2. So we have to ask ourselves, what would we multiply together to get -2, but add to get -1? And so we know that we have to use 2 times 1 to get 2. And when we add them together, I need a -1, which would force our 2 here to be negative. So we're going to use these values from our sum and product to rewrite our quadratic equation with our 4 terms. So I chose to write 2x squared minus 2x plus x minus 1 equals 0. Again, divide the equation to 2 parts and ask yourself what's the most you can divide out from each part of your equation. The first part we know is we could divide out a 2x, so that would leave us with x minus 1. The second part we just can divide out a 1, and that leaves us with x minus 1. Notice how x minus 1 is a common factor. So if I divide out an x minus 1, I would be left with 2x plus 1. So my two factors are x minus 1 and 2x plus 1. Again, we need to take each factor and set it equal to 0 and solve. So if we're working with x minus 1 equals 0, we could easily add 1 to solve for x. For our second factor, we have 2x plus 1 equals 0. Here we'd have to do 2 steps. We would need to subtract 1, so we have 2x equals -1. And then we would have to divide by 2, so our second answer would have to be x equals -1/2. For number 3, we've got x squared plus 5x equals 0. If we're sticking with our fail-proof way of factoring, we'd have to add in a constant term of 0 so we can follow our pattern. So we could take 1 times 0, which is 0. So we have to think about what two numbers would we multiply together to get 0, but add to get 5. Hopefully remember that 5 times 0 equals 0, and 5 plus 0 equals 5. So we can use those values to help rewrite our equation with 4 terms. X squared plus 5x plus 0x plus 0 equals 0. We know 0x plus 0 is 0, so we don't have to worry too much about this part of the equation. The first part, though, we have x squared plus 5x. So we know we can divide out an x from each of those terms. So we're really working with x times x plus 5 equals 0. We have our multiplication problem here, so we have our two factors of x, and x plus 5 equals 0. Now we just need to set each factor equal to 0 and solve. Well, x equals 0, that's solved for. If we have x plus 5 equals 0, we just need to subtract 5, and we have x equals -5. Here we have x squared minus 5x plus 6 equals 0. We can start working on taking the leading coefficient of 1 and multiplying it by 6. So we have to think what times what gives me 6, and what plus what will give me -5. Hopefully we can remember that -2 times -3 will give me 6, and -2 plus -3 will give me -5. We're going to rewrite our equation now so it has our 4 terms, and so I chose to write it as x squared minus 3x minus 2x plus 6 equals 0. Split your equation in 2 parts and try to do your factoring. What's the most you can factor out from each of those 2 parts of the equation? The first part would be dividing out an x. The second part would be dividing out a -2. If we notice, we have a common factor of x minus 3. So that would give us the factors of x minus 3 times x minus 2 equals 0. We would set each of the factors equal to 0 and solve for x like we normally would. So if it's x minus 3 equals 0, we would add 3, so x should equal 3. If it's x minus 2 equals 0, we would add 2, so x equals 2. For number 5, we've got 2x squared equals 12x minus 10. Again, if we're going to solve this by factoring, we need to make the equation equal to 0. So I'm going to move my terms of 12x minus 10 to the left side of the equals. So I would have to subtract 12x and add 10. So I'm now working with 2x squared minus 12x plus 10 equals 0. Again, now I'm going to multiply my leading coefficient times my constant. So 2 times 10 would be 20. And so I have to think about what two numbers I could multiply together to get 20, but then add to get negative 12. Well, on second thought, those are getting to be larger numbers. And I'm looking at my values, and I see I have 2, 12, and 10. All of those have the same factor of 2, so we're going to make this a simpler problem and try that method again. If I divide out a 2, I'm now working with x squared minus 6x plus 5. So my method would be 1 times 5, which is 5. So what times what gives me 5? But it would also add together to give me negative 6. These values are much smaller, so it's easier for me to think of my patterns. So I remember that if I want to multiply to get a 5, but add to get a negative 6, I would have to remember that negative 1 times negative 5 is 5, and negative 1 plus negative 5 is negative 6. So I'm going to rearrange my values. So I have x squared minus x minus 5x plus 5. Remember, we're still keeping that common factor of 2 in front of our equation. We have to keep it there to keep the equation equivalent to where we started from. We're going to continue the factoring process like we normally do. What can we divide out from these two terms? What can we divide out from these two terms? The first part would be dividing out an x. So I'm left with x minus 1. Our second part, we could divide out a negative 5, so it'd also be left with x minus 1. I can see they have a common factor of x minus 1, so I can rewrite this as 2 times the quantity x minus 1 times x minus 5 equals 0. These are my factors, x minus 1 and x minus 5. I need to take each of those factors and set them equal to 0 and solve like I normally do. So x minus 1 equals 0, I would add 1, so I'd have x equals 1. And here I'd have x plus 5 equals 0. I would need to subtract 5, so x would equal negative 5. For number 6, we have negative x squared equals 6x plus 8. Again, to solve by factoring, we have to have an equation equal to 0. Typically, we use leading coefficients that are positive for our x squared term. So what I'm going to do is I'm going to add the x squared to each side to make it a positive value. So I would have then 0 equals x squared plus 6x plus 8. I can now use my pattern that I normally do for my factoring. So 1 times 8 is 8. So what two numbers would I multiply together to get 8, but add to get 6? Well, that would mean I would use a 2 and a 4. 2 times 4 is 8. 2 plus 4 is 6. So I'm going to rewrite my equation with my 4 terms. I'm going to write x squared plus 2x plus 4x plus 8 equals 0. And again, ask myself what's the most I can divide out from these two terms and the most I can divide out from those two terms in my equation. The first two terms I could divide out an x. The last two terms I can divide out a 4. So if you notice, they both have a factor of x plus 2. That's our common factor, which means our other factor would have to be x plus 4. Once you have your two factors, you can set them equal to 0 and solve like you normally do. If we have x plus 2 equals 0, we could subtract 2 from each side and end up with x equals negative 2. If we have x plus 4 equals 0, we could subtract 4 from each side, and we are left with x equals negative 4. And that ends our lesson for 9.1. Again, we worked on simplifying our radicals using perfect square factors. We worked on adding, subtracting, multiplying, and dividing radicals. And then we did a quick refresher on how to factor your quadratic equations using the fail-proof method. For your homework for tonight, you're going to practice those concepts on your page 368 with the problems listed above. Remember, you can always go back to any point in this lesson and rewatch any topics that you had questions on. And if your questions are still not clarified, please come in before school, after school, or during one of my free periods, as well as asking questions in class to make sure that you have mastered the concepts.